Okay, good morning everyone. Dr. Nat here. So we are going to do lecture for week 2. We are going to continue a bit on gain and attenuation. Just a little recap, and then I'm going to teach you on AM modulation, the first topic on modulation for this class. Okay, so let's start. I hope it's recording and you can hear me clearly. So recap on dB. So dB, remember dB is in logarithmic scale. So if you don't remember about this, I'm telling you now, dB is in logarithmic scale. That is why when we in linear form, we multiply, right? In linear form, we need to multiply the gain. But in dB, it becomes a summation because it is in logarithmic scale. So you can't actually multiply it when it's already in dB. Now to convert the linear gain to become dB, remember there was an equation involved, which was 10 log base 10 of gain to get gain in dB. So this is where the log came from. So you are converting a linear gain or linear attenuation into a dB scale or dB form. Okay, decibel. dB is decibel. Okay, so remember from previous lecture, we have a system. Okay, this is our system. And you have your loss stage or your attenuator. And this is the symbol for amplifier or gain. And this is your loss or attenuator. And this is your gain. So you have something that is connected subsequently. You have your attenuator gain. So when this is combined in this way, if it is in linear scale, you would multiply like this. Okay, so you have A1 times A2 times A3 times A4 to get a total, the total gain or total attenuation. At this point, we don't know if it's going to be a total gain or total attenuation. So it's just A subscript T. So here we have A1 as 0.1. So anything that is less than 1 is going to be attenuation. Anything that is greater than 1 is going to be gain. This is less than 1, this is attenuation, and this is greater than 1, therefore it is gain. So you multiply these together and you get something that is greater than 1. Therefore, the total system is amplifying the input. So from V in, you are expecting your V out to be greater than V in because your total attenuation is greater than 1. And it is 6.75. Okay, remember this is just a recap. If you don't understand what's going on here, you need to watch the recording. It's already posted on Putra Blast. Okay. So when finding the total gain or net gain, we can add the amplifier in dBs because the net gain is a multiplication of amplifier gain. Remember, multiplication in linear scale, and you add when it is in log scale or in dB. Okay, that's just a little recap. Right. So this is something different than dB. It looks the same. It's called dBm. Sorry, it's called dBm. Sounds like dB, but it has the M. Okay, so what's the difference? Okay, remember our dB is like this. Okay, I'm going to just write it down first. Okay, this is log base 10, and then we have A in linear. So this is for voltage, if I'm not mistaken. No, wait, this is for power. So remember you had two equations. One was for power, the other was for voltage. For voltage, it is 20 log 10 of A. Okay, so your system can be calculated in terms of power or your system can be calculated in terms of voltage. Depending on what the question gives you, you decide whether you need to calculate this in power or in voltage. Sorry. Okay, so that is dB. Now this is dBm. When a decibel value is calculated by comparing a power value to 1 milliwatt, the result is called dBm. So it's somewhat like dB, but now it's comparing to dBm. Sorry, it's comparing to 1 milliwatt. Previously, what we were comparing to, let me rewrite this, this was P out over P in. And this was V out over V in. This is a ratio of output versus input. This is also ratio of P out versus P in. Now this is also a ratio, but the ratio is between 1 milliwatt. So P out versus the ratio of 1 milliwatt gives you dBm. It's still a ratio, but now it's comparing to something that is fixed. Fixed, eh? This one was not fixed. It depended on our system. What was the P in, what was the P out? So this is the ratio of A. This is a ratio with respect to 1 milliwatt, which is a fixed value. Now, if you change your system, would the equation be different? No, the equation will still be 1 milliwatt because that's the definition of dBm. Okay? Oh, I can't erase this. Oh. Right. Okay, so you still have the log here. So it's still something in logarithmic scale. Okay, so let's do an example. The output of a 1 watt amplifier, okay, 1 watt, expressed in dBm. So this is an output. So this is P out, right? P out is 1 watt, expressed in dBm. So, okay, I would actually write this as P subscript dBm equals to 10 log P out in watt, and 1 milliwatt in watt is just 0.001. Okay. And then how do we calculate this? You just use your calculator. And I forgot my calculator again today. So 1 divided by 0.001 will give you 1000. And then you log base 10 of this. So log base 10 is just simply log in your calculator. You have to do extra steps if you want it to be a different base, but the default is log base 10. So log of 1000 will give you 3, and then 3 times 10 is 30 dBm. So the output expressed in dBm is 30 dBm. Now, what is the function of converting this into dBm? It's actually for optical engineers to design a system. When they have something in dB and dBm, it's a lot easier to calculate the gain and the attenuation and what you need to get rid of. It's just easier. So this is like the starting point to become a designer for optical systems. Okay, so you can't really see the beauty here now yet, but you need to bear with it. Okay, so this is how you build up your fundamentals. Okay, so it is very important. We have an important note here. To combine 2 or more power levels given in dBm, the dBm units must be converted to milliwatt or watt unit. To combine 2 or more power levels given in dBm, let's say you have 5 dBm and you have 3 dBm, and you want to combine these two. What is the result? You can't just simply add them together. It doesn't work like dB. So to combine this, you have to convert it first to milliwatt or watt, and then add these two values together and then convert it back to dBm. Okay, so to convert dBm to milliwatt, you use this equation, 10 to the power of dBm value divided by 10, and then this will give you something in milliwatt. Milliwatt. You need to double check if it's milliwatt or watt. Okay, so never add or subtract in dBm. Okay, penting, important. Okay, next example. A microphone has an output of minus 50 dBm. Okay, same story, just like right now, like before, except that now we have it in dBm. Just now was in watt. Where the actual output power is, so we have something in dBm, we want to convert it to power, the linear scale. So 10 to the power of, oh sorry, I need to do this from the start, P dBm equals to 10 log P out in watt over 0.001 in watt. This is our starting point, and this is what we have, minus 50, 10 log, and then we need to find out what P out is in watt, and this is 0.001 in watt. I'm not happy with my handwriting. Okay, so minus 50 divided by 10. So you bring this guy over here. So what you're going to get is minus 5, right? Then you're left with minus 5 log P out over 0.001. Okay, what's next? How do we get rid of log? Remember, I told you if we want to get rid of log, we need to do the exponential on both sides. So if I do the exponential on both sides, we're going to go over here, okay? Over here. So 10 to the minus 5. And then we have 10 log P out over 0.001. So when we have 10 to the power of log, it basically cancels out. And what you're left with is P out over 0.001. So because this is in watt, so you would multiply this guy with 0.001. Okay, I'm just going to write this down so that you don't get confused. So that would give me 10 to the power of, yes, ada orang nak, someone is asking or no? So this is 3, 1, 2, 3. 10 to the power of minus 8 is P out. Okay. So I want to make this nicer looking. I can just leave it like this. Okay, so this will be 10 to the power of minus 8 watt is the P out, or I can make it look nicer and make it like this. P out, this is nano. So it becomes 10 nanowatt is the answer. Okay, both answers are correct. This is just a little bit fancier. Okay, so the equation nicely is written here. If you can't follow my handwriting, it should be, it's not that bad. Okay, so any questions about this?
Ada, tapi apa 0.001 tu fix kan?
Betul?
Cuma bila buat calculation kena tukar jadi watt. Semua benda tukar jadi watt.
Yes. Okay, so what if you wanted to make this in milliwatt? We can do that. Let's duplicate this. Let's cut it over here. So this is in watt. What if I wanted my answer to be in milliwatt, right? So if this is in milliwatt,
Oh boleh.
boleh. So this
Oh dia tak adalah wajib dalam watt. Cuma
but your
kena sama.
answer will be in milliwatt. This guy will be 1. So it's basically the same thing.
Sama lah.
1 milli is 1 times 10 to the minus 3, right?
Ya. Betul.
Okay. I would keep it in watt to just to be safe, because everything is watt, is SI unit. If you use milliwatt, you can, but I fear that you will add unnecessary values, if that makes sense. So everything must be in SI lah. So the reason why they use watt is because it's like the SI unit, and everything, if you even convert it elsewhere, it's going to maintain the value as it is rather than using milliwatt, because you have that 10 to the minus 3. Okay, so watt is the safest, right? So moving on, we discovered that 1 watt was 30 dBm. Our first example converted 1 watt amplifier output, and we found out in dBm it was 30. So that doesn't really make sense, or it's not really intuitive, right? Yes, it's not intuitive at all. So if you look here, 1 milliwatt, this is 0.001 watt, which is 1 milliwatt, is actually 0 dBm. Again, it's not very intuitive. So 0 dBm is 1 milliwatt. 1 watt is 30 dBm. So let's see how it progresses. So if I times 1 milliwatt by 2, you add 3 dBm. If I times 1 milliwatt by 10, right, I'm removing one 0. So I'm multiplying 1 milliwatt by 10. I'm adding 10. Okay. What if I multiply this by another 10? I'm adding another 10. And I multiply another 10. I'm adding another 10 dBm here. So multiplying by 10 gives you a 10 dBm increase. Multiplying by 2 gives you a 3 dBm increase. Okay, so this is like the pattern that we discovered here. Okay, so let's see if it works somewhere else. Times 10 over here plus 10 dBm, times 10 over here plus 10 dBm, and so on. You can see that the progression is every time you times 10. Okay, so this is positive values of dBm. Where do we get negative values? Negative values is anything that is less than 1 milliwatt. Because why? 1 milliwatt was 0. That was like the reference. Anything less than 1 milliwatt will give you a negative dBm. So this one is divided by 2. Okay, you get minus 3. What if 1 divided by 10? You get minus 10. So anything that is divided by 2 minus 3 dBm. Anything that is divided by 10 is minus 10 dBm. Okay, so that is the pattern if you want to memorize. Otherwise, just convert it using the equation. Okay.
Betul.
Yes.
Yang tadi doktor cakap macam kalau dia apa nombor perpuluhan tu bukan negatif dBm.
Nombor perpuluhan. Cak lagi sekali. What's the question?
Kalau gain dengan attenuation macam more than 1 or less than 1 kan untuk okay, yang untuk negatif dBm tu nampaklah bila perpuluhan dia jadi negatif kan.
Less than 1 milliwatt. Ni ada beza. There's a difference here. This is what? This is what? This is milliwatt.
Oh, milliwatt.
Hmm.
Oh, okay. Baru nampak.
Less than 1 milliwatt. Yang ni above 1 milliwatt.
Oh.
So the definition.
Okay. Dia punya tengah-tengah tu dekat milliwatt lah kan?
Yes. For gain and attenuation, the baseline was 1, right? Here it's 1 milliwatt.
Oh, okay. Nampak.
Okay.
Doktor, satu lagi, apa slide width tu ni doktor tak bagi lagi rasanya.
Dia ke? Sekejap.
Dekat Putra Belah tak ada, dekat group pun tak ada. Tapi yang doktor tengah ajar sekarang ni ada kat ujung-ujung week 1 juga. So okay je.
Oh, lah. I didn't share. Let me share now. Okay, let's stop sekejap. Let me unshare. Don't know how I forgot about this. Thank you for reminding me. Teaching. Lecture week 2. Okay, sorry about that. I already shared on WhatsApp. You can access that for your scribbles. Okay, entire screen share. Sekejap. Okay. Let's continue. Any questions from anyone? No questions? Okay. If you have any, you can interrupt anytime, as usual. Okay. Given two devices, one has an output of 0 dBm. So right off the bat, I already know this is 1 milliwatt. While the other has an output of 5 dBm. Okay, so this one I can't convert because it's not times 2 or times 10. So I need to do it using the equation. Find the total output of both devices in dBm. So the first thing you need to do is convert dBm to milliwatt. Okay, so let's do that. So log P dBm equals to 10 log of V P out over 0.001. Okay, so this is going to be in watt. So this is 5, this is 10, this is log P out. So I have 5 divided by 10 is going to be 5. 10 to the 5 P out over 0.01. Is correct? Yeah. So 10 to the 5 times with 10 to the minus 3. I get 10 to the 2, which is my P out. So this is going to be in watt. Okay. 10 to the 2 is 100. Hopefully that's right. Okay, so P out is it 100? 100 watt. I'm not very convinced with my math, but I think this is right. The other is 1 milliwatt, and this is 100. So this is kind of big. Wait, did I do this wrong? P dBm 10, 5. Okay, so if 10 dBm is, okay, so this is big. 10 to the 5. This is 0.5. Why didn't anyone say anything?
Saya pun tak perasan betul.
Okay. Okay, so 10 to the power of 1 over 2 is, I don't know. So let's just hope the math solves itself. 0.001 in watt. Okay, so this looks better. And then this is your P out number 1 or maybe number 2. So the P out total is P out 1 plus P out 2 in milliwatt. So one is 1 milliwatt and the other is, I would do this everything in watt, so that's easier. And you have something over here plus P out number 2. So you have something in milliwatt, in watt, and then you convert it to dBm again.
3.16 sana sini.
This one. Ke this one?
3. Final answer 3.16 milliwatt.
Milli.
Milliwatt times 10 power of negative 3.
Okay. Okay. Thank you. And then we have to convert it back to dBm. Then 3.16 times 10 to the minus 3. Oh, I forgot the log. Divided by 0.001. Okay, so you will get something in dBm. This is number 2 and this is number 3. First, you convert dBm to milliwatt. Second, you add the P out 1 and P out 2 to get the P out total in watt. Third is you convert the total output in watt to dBm. Okay.
Kejap.
Oh, I have
Hmm, rasa macam silap ke tadi. Kejap. Sebab tak perasan P apa? P out, P total.
Oh, it's okay. I have it here.
Faham.
Okay, 1 milliwatt. This is 3.16 milliwatt. And then the
Ah,
total is 4.16 milliwatt. And then you convert it back to dBm. Okay. So this is the
1 tu sebab 0 dBm tu
yes. But you can also do it using the equation. I just remember that I told you 0 is 1 milliwatt. So I just took it from here. You can also do that. But you can't pick out this value from the table. The 5 dBm is not possible, so you have to use the equation. Okay, is everyone okay? Or confused?
confused dengan soalan.
Confused dengan soalan.
Macam mana nak tahu kena buat step tu kan. Sekejap. Faham
Okay.
soalan ni.
Okay, so your friend Syafiq ni.
Oh,
Syafiq
ya.
je yang bercakap dengan saya, orang lain tak bercakap. Okay, tak apa. I appreciate Syafiq for telling me what's his concern. Okay, so Syafiq is asking, how do we know that we need to do those steps in this question? Okay, so let's go over the question again. Given two devices, one has an output of 0 dBm and the other has a 5 dBm output. It's asking us to find the output of both devices in dBm. Both devices in dBm. Now remember that I told you it is very important that you do not combine dBm by adding them together. You have to convert them to watt unit, add them together in watt unit, and then convert back to dBm. So these are the steps that I used to solve this question. To combine two values in dBm, convert to watt, add them in watt, convert back to dBm. So this is the three steps that I use to do here. So I convert this to milliwatt or watt. That was the first step. Second, add them together in watt. And then 3, you would convert it back. So I'm just using the steps for adding two dBm values together. Is that okay? Still confused?
Okay. Baru
Okay.
nampak sebab dia ada dua benda kan. So dia tak boleh tambah macam tu je kan.
No. Yes, you have to convert. Always use these steps. Important steps. Okay. For dB, yes, you can add them together. dBm, no, you cannot add them together. You have to convert back to milliwatt or watt. Okay, so let me write that down here. Note dB plus dB. Okay. dBm plus dBm. How do I do the death face? I don't know. This looks like potato, but this is supposed to be a skull. Okay, don't do this. Convert to milliwatt first. This does not look like a skull, sorry. Skull. Okay. Convert to milliwatt first. Okay, so dB and dBm are different. Okay, I hope everyone is clear. dB can be added together. dBm, convert to milliwatt, and then convert back to dBm. All right. So that was the end of gain and attenuation and dBm. Now let's move on to noise. Noise is an electronic signal that is a mixture of many random frequencies at many amplitudes. So the frequency is random, the amplitude is also random, you can't really fix anything, and it gets added to a signal as it is transmitted. Okay, so let's see. So this is an analog signal. We have signal plus noise, and this was the noise. Okay, this was the noise. You can see that at certain points, you can actually see like the peak from the noise is present in the peak of this guy. We also have signal and noise in digital signal. So digital signal is not safe from noise. So here, what we observe is actually the signal and noise, but when we isolate them, this is the actual signal and this is the noise. So signal has like a fixed frequency or like multiple fixed frequency and a controlled amplitude, but for noise, it's random, it's randomized. Okay, so same case over here. If it's digital, the actual signal is clean, but when it gets transmitted, there's noise added to the signal, so this is what you get. And to remove the noise so that you get a good signal back, you have to do some filtering or some modulation techniques. Okay, so this is how it looks like. Sometimes when the noise gets too big, for example, if my noise is like this, I have a spike like that. So if the spike is overlapping with the 1, with the value 1, then I'm fine. But what if my noise overlaps here? So it's giving me a false value 1 in the signal that I'm observing. So this is where the error happens because of the noise. If the noise is too big, it is perceived as a signal 1, and whatever that is decoding it is going to decode a wrong signal. Okay, so this is okay lah. This is error. Okay, so how is noise formed? Noise is formed by increasing any of these factors such as temperature, bandwidth. If you increase the current flowing, you also increase the temperature, therefore you increase the noise. If you increase the gain of the circuit, you are actually amplifying the noise. For example, you have this, and this is combined with noise, right? And your gain is super high, which means that whatever that is here is going to be amplified as well. So you're not only amplifying the signal, you are also amplifying the noise. So the higher the gain you provide to the system, the higher amplification of the noise, because it comes in a package. You can't really separate them. So you're also amplifying the noise. And if you increase the resistance of a circuit, you are also increasing the noise. So these are the factors that you need to consider when designing a circuit to, make the noise a minimum. Okay. So we have two types of noise, internal and external. So let's talk about internal noise first. So internal noise comes from electronic components in a receiver such as resistors, diodes, transistors. Your components, your basic components actually are very noisy. So the noise caused by these components are called thermal noise, caused by a phenomenon called the thermal agitation by random motion of free electrons in a conductor caused by heat. So that's a lot of definition. Basically, you just need to know that your basic components contribute to thermal noise. So often known as white noise or Johnson noise, this is the noise that you use for babies to sleep because it's very randomized. So the level can be reduced by limiting bandwidth or filtering. Okay, so we have an equation to calculate this thermal noise. So in an open circuit, this is an open circuit. Why is it open? Because it's not connected. Okay, so this is an open circuit. So I want to find out what is the noise of this resistor. Because this resistor has resistance, and remember resistance contributes to noise. Current flow also contributes to noise. Temperature also contributes to noise. Bandwidth also contributes to noise. So everything is encapsulated in this equation. So the noise voltage in RMS is equal to square root of 4K temperature, bandwidth, resistance. K is a constant. Okay, Boltzmann constant. You don't have to memorize this. It's going to be given. The constant is going to be given. But the equation, you need to know how to use it. Voltage noise in RMS, square root for Boltzmann constant. Temperature in Kelvin. How do you convert Celsius to Kelvin? Add 273 plus Celsius. Okay, this is supposed to be degrees Celsius. Bandwidth in Hertz and resistance in ohms. Okay, let's do an example. Okay, what is the open circuit noise voltage across, this is Vn, across a 10 kilo ohm resistor over the frequency range of direct current to 20 kilohertz at room temperature? Okay, so we have this equation. K, we don't have to care. We have to care about T, B, and R. So what are the values given by this question that we need to use in this equation? So T is temperature in Kelvin. We have temperature, which is 25. So to convert to Kelvin, it is 273 plus 25. So you will get something in Kelvin. Bandwidth is already in kilohertz. I just need to get rid of K, 20 times 3 hertz. And resistance is 10 kilo ohm. So that is 10 to the 3. Okay, so how did I know that this 20 kilohertz is the bandwidth? Because it mentions frequency range. Remember what the bandwidth formula is? F2 minus F1. This is a frequency range. The range is between F1 to F2. So frequency range is also the same as bandwidth. So that is how I decided, okay, so this frequency range is actually the bandwidth for this question. Okay, so did I do this? Yeah. Okay, so 4 times Boltzmann constant, 273 plus 25. This is in K. So this gets cancelled out. 20 is in hertz. And this is, what is this? Ohms. Okay, so you multiply this, square root this, and you will get something in volt. Okay, let's take a 5-minute break. Let's come back at 11:47 a.m. If you have any questions, you can ask them now. Otherwise, please take your break. Okay, so let's continue. As I mentioned to you before, there are two types of noise, internal and external. So yeah, let's write it here. We have external and internal. And then under internal, we have uncorrelated, which I cannot spell. Uncorrelated and correlated. Okay. So the one that we discussed, which was thermal noise, from a basic component in the circuit is uncorrelated noise. Thermal noise is uncorrelated noise. So in addition to thermal noise, semiconductors produce short noise, transit time noise, and flicker noise. So there's a bunch of other noises. All of these are called uncorrelated noise. So short noise is independent of temperature. Thermal is dependent on temperature. Short noise is independent of temperature. It is typically in bipolar transistors, also white noise that contains all frequencies and amplitudes over a wide range, just like thermal noise as well. The amplitude of the noise voltage is unpredictable but follows a Gaussian distribution curve. So I don't know if you know what Gaussian distribution curve is, but I think you've learned this in signal processing class. So it's just like a peak that is very cute. So that is a Gaussian distribution curve. So the amount of RMS noise current in a device for short noise is given in current. So IN is the square root of 2QIB. Q is the charge on an electron, I is direct current in amperes, and B is bandwidth. So this is your equation for RMS noise current for short noise. Okay. So another uncorrelated noise is transit time noise in micro devices that produce more noise as approaching cutoff frequencies. I don't know if you know what cutoff frequency is, but we will learn about it later. And then we have flicker noise or excess noise, noise due to defects that decreases with frequencies. So this guy approaches cutoff frequency. This one is noise due to defects that decreases with frequency. So going higher frequency, going lower frequency, getting higher temperature, all of this contributes to noise. So what is not noisy? So basically you're living in a very noisy world. Something to think about. Okay, so another one is correlated noise. Just now we talked about uncorrelated noise, was very noisy, random frequency, random amplitudes. Correlated noise is very intentional. If I can use that word, it's intentional, meaning to say that it only works, it produces a value that we can predict. That is correlated noise. So intercorrelated noise is intermodulation distortion. Intermodulation is products of two input signals. We have frequency 1 and frequency 2. So let's imagine this. This is frequency 1. This is frequency 2. These are signals in the frequency spectrum. Yes, they look like sticks in the frequency spectrum. In the time domain, they look like waves. In the frequency domain, they look like sticks because they basically represent a single frequency. Okay, so this is your input. These are two signals, F1 and F2. F1 and F2. And then because of intermodulation distortion, the F1 and F2 produces F1 plus F2, F1 minus F2. So this is V sum and V difference. And intermodulation distortion can also interact with harmonics. So harmonics is basically an input signal of a device, and that device has a high nonlinearity which produces harmonic signals. Harmonic ni macam a repetition of that signal. So the repetition is 2F1, 3F1, 4F1, but the amplitude decreases over the higher the harmonics, the lower the amplitude. So this is harmonics. Intermodulation distortion and harmonics are two different things. Again, let me rephrase this. Intermodulation is when two signals combine, they produce sums and differences. And then we have harmonics from a single frequency, from a single signal that produces more replicas of the signal as well. But the replica is lower in amplitude, but at a multiplication of the frequency. So it's 2, 3f1, 4f1 is a multiplication. It replicates the signal, but at lower amplitudes. So the further away the frequency is, the lower the amplitude is. So these are two different things. Now, IMD can also happen with harmonics. So when that happens, how to say this? Caca merba lah kan. Caca merba in English is what? It's chaotic, right? So let's see. So internal noise, correlated noise, intermodulation distortion. So let's see. We have two signals, F1 and F2. Due to intermodulation, any nonlinearity generates new signals. This is IMD. Okay. Any nonlinearity generates new signals, F1 minus F2. From this combination, you have this and this, F1 plus F2, F2 minus F1 from these two signals. And then these new signals, okay, the one in red, begin to mix with some of the harmonics generated by the nonlinearity as well. So you are mixing F1 plus F2 and F2 minus F1 with harmonics. So what you're going to get is 2F1 minus F2, 2F1 plus F2, you have 2F2 plus F1, blah, 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 blah. You have a lot of this. Okay, so this is what happens when correlated noise occurs due to nonlinearity of your device. Now, there's a question. How do we know our device is nonlinear and causing all this noise? Basically, it's anything that they define as nonlinear. Okay, how do I say this? Okay, a nonlinear device, okay, is anything that takes two inputs and generates one output. Two input or more, but the output is 1. Okay, if it is a linear device, the input is 1, the output is 1. The input is 2, the output is 2. But for non-linear device, there is some math happening here, math equation that converts these two inputs to a single output. So that is roughly the definition of a non-linear device in mathematical terms. Okay, so I hope I didn't confuse too much. Okay, so we will talk more about this. So just bear with me. What you need to know here is intermodulation distortion can make sum and differences from two signals, and these sums and differences can interact with harmonics. What is harmonics? Okay, I already explained what harmonics is. They interact with harmonics to produce more new signals. So these new signals are all noise. What we wanted was just these two signals, but we get a lot more than what we wanted. Okay. Okay, so external noise is pretty simple. It's something that we can't control. It's not from our device. It's from the outside. It's not internal. So one of it is industrial noise. Noise pulses of large amplitude occur whenever a motor or other inductive device is turned on and off. Machines, basically. Machines cause noise to your circuit. Kind of odd, but it does happen. And then we have atmospheric noise, can't pronounce, atmospheric noise or static. The electrical disturbances that occur naturally in the Earth's atmosphere, for example, lightning, has the greatest impact on signals at frequencies below 30 megahertz. So if you have a lightning occurring, your signal is operating below 30 megahertz, it's going to be impacted. And then we have extraterrestrial noise, alien noise, or I would say space noise. So anything that is outside the Earth atmosphere that could also contribute to noise, especially for big machines. Not your circuit. Your circuit is going to be insignificant compared to extraterrestrial noise. But big machines, planes, stuff like that, yes, they are exposed to this kind of noise. Okay, so that was internal and external noise. Internal, you have uncorrelated from your devices, and you had correlated, which was something that you could actually predict. We talked about correlated noise, intermodulation, distortion, and harmonics. And then for external noise, it was noise from machines, from the atmosphere, and also from space. Okay, so now moving on, let's talk about signal to noise ratio. So it's a lot of new terms for you because you're just starting, right? So signal to noise ratio is called SNR. So if anyone has any questions, please feel free to interrupt me. Okay, we have another hour. So SNR, so signal over noise, signal to noise ratio. The R is ratio. So signal to noise ratio can be voltage or in power. So the voltage signal over the voltage noise, or the power signal over the power noise. So to convert SNR in dB, this is for voltage times 20. And to convert SNR in dB for power, this is times by 10. So same equation for AdB, same equation for amplifier and attenuation as well. So SNR also uses the same equation. Okay, so this is an example of high SNR. This is an example of high SNR. The signal, this is the signal to noise ratio is far. Okay, the distance is far. Therefore, the ratio is high. So you have a high ratio of signal to noise, high SNR. If the difference is small, the signal is small compared to the noise, meaning to say the ratio is going to be small. If the ratio is small, therefore you would get low SNR. If the SNR is less than 1, that means the noise is greater than the signal and the dB value will be negative. Okay, so let's do an example. Assume the signal voltage is 1.2 microvolt and the noise is 0.3 microvolt. So SNR is basically signal over noise. So 1.2 micro over 0.3, you get 4. So this is the SNR value. And if we want to find out in dB, this is in voltage. So therefore SNR in dB will be 20 log of 4, something in dBm. Okay, simple. As long as you know how or when to use the equations. So we talked about SNR. SNR is signal over noise. So we have another two terms called noise ratio and noise figure. So noise ratio is SNR input over SNR output. SNR input over SNR output. What is SNR input? The signal to noise ratio of the input. Your input, let's say this is V in, you also have V in noise. So what is the SNR? The SNR is the SNR input. And then the output, you have V out noise. So that is going to be your SNR output. So the noise ratio is SNR output over SNR input over SNR output. It's flipped. We always see out over in. In this case, it's input over output. Yeah. So this is noise ratio, and then when the noise factor is expressed in noise ratio expressed in dB is called, this is ratio. It is called noise figure, NF. So this one we use 10. Okay, any questions? No questions?
Tak ada, tak ada.
Okay. Everyone sleepy already? Take a deep breath and wake up because we have 1 more hour to go. Okay, an RF amplifier has an SNR ratio of 8. Okay, at the input. Okay, so we already know this is SNR input and an SNR ratio of 6 at the output. So this is SNR output. What is the noise ratio and noise figure? Okay, NR is this one, SNR input over SNR output. So we already know what it is. So input is 8 and output is 6. And then the noise figure, NF, is just 10 log of 4 over 3. 4 over 3. Okay, so whatever that is, this is going to give you in dB, not dBm. Okay, I forgot to put this somewhere. This is dBm. Okay. Okay. Moving on. Okay, so enough of gain attenuation, enough of noise, enough of SNRs. Let's start with amplitude modulation. Okay, sekejap I need a minute. Let's take 5-minute break again. Sorry. PM. Okay, get some drinks. Keep yourself alive and awake. I'm going to be back in 5 minutes. Okay, sorry about that. Okay, let's continue. Share slide. Am I sharing slide or not? Oh, I am. Okay. Right. Okie dokie. Let's start with amplitude modulation. Okay, I want everyone to focus. This is your first modulation topic. So what we will learn is amplitude modulation fundamental, coefficient of modulation and modulation index, and modulation percentage. AM voltage, AM means amplitude modulation, voltage, power and current distribution, and time domain analysis. And then we have circuit for AM generation, AM transmitter system and measurement. I believe we can cover these three. Maybe this one for next class. Okay, so what is sekejap Alamak. Okay. Alright, so amplitude modulation is the information signal varies the amplitude of the carrier sine wave. Information signal, we vary the carrier sine wave. Now, the question is, what is information and what is carrier? Those two terms. Okay, so we have a modulating or information signal. In this case, let's say our information signal is a single frequency wave. Okay, so this is A? A is, okay, it doesn't say. So A is assuming is message signal. This is your signal. Your signal is ting, one frequency. So that is your signal that you wanted to transmit. Because why? Because why not? You wanted to transmit this message, you need a carrier. So how should your carrier be? Your carrier wave. Your carrier wave must be higher frequency and higher peak and higher voltage peak than your modulating signal. So your carrier, let me write it here. Carrier wave, the condition needs to be higher frequency than a message wave, higher voltage peak than message wave. For example, your message wave is 1 volt in peak. Your carrier wave needs to be more than 1 volt. If your message signal has a frequency of 10 Hz, your carrier wave needs to be more than 10 Hz. So that is the condition for amplitude modulation. Message wave or message signal has to have lower amplitude, lower frequency than carrier wave. Okay, so now that we know the condition for these two waves, what happens when we modulate these two waves together? We will get an amplitude modulated signal, which looks like this. Okay, amplitude modulated signal. Now, if you can observe, amplitude modulated signal follows the same shape as your message. Same shape. Same shape. And if you notice as well, it looks like a mirror. It mirrors the shape. So this is your message. And down here, it mirrors your message. So what you get is like a symmetrical envelope, right? This is your message. Inside is your carrier wave. Inside is your carrier wave. Okay. Now, what has changed about the carrier wave? The frequency has remained the same, but the amplitude of the carrier wave has changed. Amplitude of carrier wave changed. That is why it is called amplitude modulation. The message signal has changed the amplitude of your carrier wave. That is how it encodes message into the carrier wave, by changing the amplitude. Okay. Let me explain this again. If you didn't get it the first time, I want you to focus and hear it another time. Okay, there are two waves that we need to do. When we want to do amplitude modulation, we need to have two waves. The first wave is called modulating or information signal or message wave. It can be anything. It can be message, it can be information, it can be modulating signal. Those mean the same thing. Modulating signal, message signal, information signal. And then we have a carrier wave. So carrier wave is just carrier wave lah. There's no other terms for that. It's just called carrier wave. What is the condition for a carrier wave? Carrier wave needs to be higher in amplitude and higher in frequency than a information signal or message signal or modulating signal. Carrier wave needs to have a higher peak, higher amplitude, and higher frequency. Now, when we have these two conditions met, we can modulate this signal and transmit. When we combine the message signal and the carrier wave, okay, this is my carrier wave and this is my message wave, message signal. Okay, when we combine the message with the carrier wave, what happens is something that looks like this. Now the frequency is not changed, but the amplitude is changed. The amplitude of the carrier frequency has changed according to the message. Okay, so this is called AM wave or amplitude modulated wave. It follows the shape of the message. Okay, here I have a note here. The carrier frequency remains constant. Amplitude varies in accordance with modulating signal. Okay, moving on. So to do amplitude modulation, you need an AM modulator. So AM modulator is like a circuit. Okay, we have not discussed the circuit yet, but let's just imagine it's a box. So the AM modulator, your device or your circuit, what you need to feed into the AM modulator is a modulating signal, your information, and your carrier wave. Remember, carrier wave, higher amplitude, higher frequency. When you have these two input together, you pass it through this circuit or this AM modulator, what you're going to get is the AM modulated signal. So this is your modulating signal. This is your carrier wave. Again, peak is higher, frequency is also higher. There's more cycles per second. This is less cycles per second. So the frequency is lower. Combining these two, you get an envelope, AM wave. So again, the shape follows your message. You can see that the shape is exactly the same, except that my drawing is bad, but you can see that it's actually the same. Okay. Oh. Okay, and it is symmetrical. So they will mirror the top and the bottom. Inside the AM wave is your carrier. Your carrier will be modulated according to the amplitude of your message. Okay, so you can see that the carrier actually has a fixed amplitude, right? It's not fixed, but it has a fixed peak. So it goes up and down, up and down, up and down, but every time it goes up and down, the peak is the same. Let's say this is 1 volt. This is -1 volt. So the midpoint, let me use a different color for this. The midpoint for your message signal is 1 volt. This is the midpoint for your message signal. This is -1 volt. This is where the carrier is supposed to be. But because it is modulated, it is becoming higher and sometimes lower. Okay, let me undo that. Okay. So this is the initial carrier. After it is modulated, it follows the shape of the message, sometimes higher than the initial peak, sometimes lower. Okay, so you get something like that, looks like this. Okay, So AM modulated signal, often called AM envelope. So it basically means the same thing. Okay, so let's do a little recap on the terms that we used. Modulating signal is the same as information signal, is the same as message signal. Anything that you want to transmit, that's your modulating signal. And the thing that carries our message is called carrier wave because it carries. It's you ride it. The message rides on the carrier wave to get transmitted. So carrier wave has high frequency, higher peak than message. When they combine, they form AM wave. Okay. Okay, any questions so far? Everyone understands the concept? Okay, all right. Okay, I'm glad. Okay, so drawing that thing, drawing the AM wave is hard. As you can observe my drawing, it was bad. So to make it easier for us engineers, we just draw the envelope and the carrier we just make like vertical lines so that we don't have to really care the frequency of the, you have to care, but to draw it, you just can just draw the vertical lines. Okay, so that is a simplified representation. So if you see me drawing it like this, just know that what I'm indicating is the carrier wave. So this is the modulating signal envelope in orange, and then equally spaced vertical lines represent constant frequency carrier sine wave. Okay. Now that we understand the concept, hopefully we can dive a bit in the math. Okay, so be ready. So the sine wave carrier, oopsie, what happened? Okay, the sine wave carrier, okay, we have another 40 minutes. The sine wave carrier can be expressed as small v subscript c, c for carrier, equals to capital V subscript c. Capital V, why is it not working? Uh-oh. Wait. Uh-oh. It's not working. Okay, bismillah. Not working. Okay. Whew. Right. So we have small v c, capital VC, sine wave, 2 pi f c t. Now 2 pi f, I think you have this, you learned this in signal. It's omega c, same thing. Omega c is 2 pi f c t, where Vc is the instantaneous value of the carrier wave voltage at some specific time. It is dependent on t. Okay. Now remember that we drew the carrier wave. I drew the carrier wave. Okay, this is an ugly carrier wave, but it's supposed to have a similar frequency throughout. So this is supposed to be a single frequency. Now, at a specific time, okay, let me draw the axis for this. Okay, this is in time domain, right? Time. Okay. So this is voltage, right? So VC is this guy, the peak voltage. Okay, of course, this also extends down here. This is minus VC. And the VC, the small VC, is telling me this is how it behaves over time. Okay, let's say my axis starts from 0 up until 100 seconds, maybe. Okay, let's just stay with that. And FC, the frequency is fixed. Remember, we have a carrier frequency. Let's say the FC is 1000 hertz or 1K, okay, 1000 hertz. So assuming I have these values, so this is 1 volt, let's just say, okay, 1 sine of 2 pi 1000 hertz and then T. Okay, if I want to know what is the value here, I need to find out what the T is. What is the T? Let's say the T is 20 seconds. So I plug in, VC is 1 volt, right? Sine, whoops, that's not a sine. That's sin. Sine 2 pi 1000, and then T, I wanted to know what is the value of VC at this particular point. So it's 20 seconds. Okay, 20 seconds. So using my trusty calculator, I'm going to plug in the values and I get some value. So let's say the value is 0.7 volt. So this is the function of this equation. It tells you at a specific time what the value of that wave is. So let's say I want to find out what the value is here. Or obviously this is like the peak, right? So it's got already 1. So this is 1, this is 1. So at this time, you already know the value. But at other times, that's not part of the peak or the dip. You have to use the equation. So that is what this equation is telling you. Okay? Again, let me repeat myself here. VC is the peak of your carrier wave, and the dip. So obviously, we're going to use the positive sign. So VC is the value amplitude 1. It can be some other value depending on the question. In this example, my peak is 1 volt. It can be 10 volt, it can be 5 volt, depending on the question. 2
Betul.
pi, yes.
Dalam radian ke pi tu?
Apa? Lagi sekali?
Pi tu dalam radian ke?
Betul.
Kalau 2 pi dia jadi sin 2 pi jadi kosong.
Betul. Sin 2 pi jadi kosong. Kenapa?
Yang ni just let's say kan 0.7 tu kan. Okay.
Okay, so let's say the time is 0. The time is 0, so the sign is 0. Sign of 0 is 0, I think. Sign of 0 is 0. So your value is 0. Kat sini lah. So sign of 2 pi times 1 is also 0. So your value is 0 at time equals to 1. Okay, so it depends on what this value is, what your sin 2 pi FCT is. If it gives you 0, then the value is 0. Oops. Any other questions related to this? Do we understand how to use this equation?
Sin pi memang 0 lah. Macam mana nak bagi ada value?
Sin pi memang 0.
Oh.
So you have
Sin
your
pi.
FCT.
So kalau bubuh apa pun 0 juga kan? Unless ada 1 over pi lah value.
Unless ada 1 over pi.
Sebab boleh potong.
So your T is, it can be 0.1, it can be other values. So it, kalau multiply with 2 pi, it's not going to be pi. It's not going to be a multiple of pi. Okay, tak apa. Nanti let's do an example and we will see. Let me see if I can find my calculator. Yep. Okay, so another, let's hold on to Shafiq's thought. It's a good thought. Okay, we will explore in an example later. Okay, so the sine wave of a modulating signal can be also expressed similarly. So this is the instantaneous, this is the peak modulating signal, this is the modulating frequency, and this is the specific time that we want to find out. Okay, same equation, same format, different subscript. Okay, so again, modulating signal looks like a sine wave as well, but lower frequency, lower VM, lower peak voltage. Okay. So the modulating signal uses the peak value of the carrier rather than 0 as its reference point. Okay, this is your, use a different color. This is your carrier initial shape. Kat sini, this is the This is the initial carrier. Remember? Oops, this is so bad. Let me use a bigger. Whoa, this is too big. So your carrier was initially like this. It had a fixed amplitude, right? Fixed amplitude. So the amplitude that I'm talking about is this amplitude, the peak. Okay, this guy. Okay, so that is the reference. Okay, let's undo this. Oh no. Okay, so that is the reference. Need you to visualize this properly so that you understand. Okay, so the modulating signal uses peak value of carrier, the one I dashed in blue, rather than 0 as its reference point. So this is why you see that the message, we need to use a different color, that the message is cycling between this dash line. It uses the peak value of the carrier as its reference. So same case over here, uses the dashed line as its reference. So the envelope of the modulating signal varies above and below the peak carrier amplitude. So it varies above and below the peak carrier amplitude. The zero reference line of the modulating signal coincides with the peak value of the unmodulated carrier. So basically these 0.1, 2, 3, they are saying the same thing. It's emphasizing that the modulating signal can only modulate here, can only modulate at the reference line of the peak carrier signal. Okay, so these 3 points mean the same thing. So the amplitude of the modulating signal should be less than the amplitude of the carrier. So what if the amplitude was higher than, what if Vm is higher than Vc? What would happen? Let's see. Let's draw this in a different color so that we don't get confused. So if my modulating signal is higher, my Vm is higher than Vc, let's do this in green as a reference. That would mean that it would extend like that. And this would be overlapping like this. What would happen if we have something that looks like that? It will cause error. So again, I'm trying to draw a skull. Let me try again. A skull. Let me write this just to make sure you guys understand. So this is error. We don't want this. When you have the overlapping like this is not good. Okay, so the green is not good. So the modulating signal should not overlap. So we have this gap here. The gap is good. Halal gap, Right, moving on. Kalau if the Vm is greater than Vc, how would it look like? Let me show you. Overmodulation and distortion will happen in the case where Vm is greater than Vc. The waveform is flattened at the zero line. Why? Because dia overlap macam tu. So it cuts out. So there's the information that is supposed to be there is no longer there because it's cancelled out. It is removed. Okay, so it's flattened at the zero line. The received signal will produce an output waveform in the shape of the envelope, but the envelope is wrong, which in this case is a sine wave whose negative peaks have been clipped off. So you will see this in your labs later. Sometimes when we overmodulate, you will get sine waves that look like this, which is wrong. AM wave that looks like kuih cara. This is a type of delicacy, Malaysian delicacy for our international students here. Kuih cara is yummy. So you can try this if you find it. So the AM wave that is error looks like kuih cara. We don't want this. This is supposed to be a skull, but it is tasty at the same time. So the received signal will produce an output waveform in this form, which is wrong. Okay, I cannot emphasize this enough. This is wrong. Okay, so if you see it, it is not good. So the ideal condition for AM is when M equals to 1 or 100% modulation percentage. Okay, so we have not covered this one yet. We will in a bit. Okay, so I think that was a lot. Let's take a 2-minute break. Okay. So if you have any questions, you can ask them. Okay.
Betul.
Yeah.
Yang ni memang pi tu macam mana nak tahu dalam radian ke bukan ni kalau dalam soalan?
Macam nak tahu dalam radian ke bukan?
Saya nak tahu kita kena guna angle unit dari radian ke pi kalau sin ke cos ke.
I think you're confusing degrees dengan
Ya.
kan? We're not using degrees here. Kita pakai radian.
Radian kan?
Okay. Nanti cuba try. Kenapa tak ada example Sekejap. Oh, I don't have an example here. Maybe next class I will have an example for that. Okay. Okay. Was that 2 minutes? Any other questions? No questions? Everyone's okay? So if I ask you this question on the modulation, you can answer. If you don't understand, you can ask me, okay? All right, so let's continue. AM envelope and complete modulated signal. So the instantaneous value of either the top or bottom voltage envelope can be computed by using equation. Surprise, we are engineers, so we have to relate everything to equations. Expresses the fact that instantaneous value of modulating signal attributably adds to the peak value of the carrier. Okay, so this was the point that we emphasized 3 times, remember? Whereby we have a carrier, blah, blah, blah. This is our original carrier, and then we have our modulating signal, whereby it will only modulate around the peak value of the carrier. And then your carrier will change its amplitude according to the message, but the frequency stays the same. So this is what we discovered just now. So now we want to represent this in the form of an equation. So first we have VC, the peak of the carrier wave, plus with the instantaneous modulating signal. Okay, peak VC, peak of C, plus with instantaneous of M. This is capital VC, which is a fixed value, and this is not a fixed value, it's a wave. So VC plus VM peak sine 2 pi FMT. Where did I get this? We discussed this earlier. So instantaneous value of VM is just this guy. Instantaneous means it's not fixed. V, when it's capital, it is a fixed value. Okay, fixed, changes with time. That's why it's called instantaneous. Why does it change? Because we have a sine wave in the equation. Okay, so again, VM is this guy. The VM, oh, sorry. Okay, so VC plus, this is fixed value, plus changing value. So this is VC capital plus VM sine 2 pi FMT. Why do we need to add VC to VM? Because the modulating signal can, the modulating signal or the shape, the reference is VC. It starts, this is the 0 point for the modulating signal. So it has to be added to VC. So if your starting point is 0, obviously you don't have to add anything. But if your starting point is VC, you have to add VC. So this is why we are adding VC. Therefore, the instantaneous value of the complete modulated signal V2 can be expressed as the following. So V2 is V1, which is this guy, multiplied by the carrier wave. because we want to multiply the modulating signal with the carrier wave inside, right? To get our AM wave. So V2 is now, V1 is this, right? V1 is this. So Vc plus Vm sine 2 pi fmt, which is basically just this, multiplied by the carrier wave. So what this gives me is Vc times with sine 2 pi fct and Vm sine 2 pi fmt times with sine 2 pi fct. So I have this and I have this. There's two terms here. One is basically the carrier wave and the other is the modulating signal times with the carrier wave without the peak. So there's no Vc here, no Vc. Okay, so if this confuses you, get rid of it. If this is helping you, use it. Okay, so I don't know which one is going to be more appealing, so I'm just putting it there. Okay, you need a way to memorize this VAM envelope or VAM equation. Find a way that works for you. This is what you need to memorize, okay? Okay, again, recapping what we just learned about the equation. We have our AM modulator. We are feeding it a modulating signal called VM, instantaneous VM, and then we are feeding it instantaneous VC. When we combine these two in an AM modulator, what we get is a VAM or our V2 just now. So VM, this is VC. So VAM is VC sine 2 pi FCT plus with the modulating signal times with the carrier signal without the VC. Okay, that's just how the equation is, and it describes our AM wave. So if you plug this in all the values, you would get this exactly. Okay, so now that we talked about the AM modulation concept, we talked about the equation. Now let's talk about modulation index. What makes an AM wave good or bad? So recall that we have VM less than VC. It needs to be, this is the condition for good AM. Okay, so modulation index is calculated by VM over VC. Now, how do you remember if VM is the top or VC is the top? Remember that VC needs to be bigger than VM, so the bigger one also always go at the bottom, right? So that's how I remember it. If that doesn't work for you, find a way that you can memorize it. Okay, so VC always bigger than VM, so VC needs to be at the bottom. So VM over VC gives us modulation index. To find out the modulation percentage, M times 100. So just basically VM over VC times with 100%. So the modulation index should be a number between 0 to 1. If VM is greater than VC, then M will be greater than 1, causing distortion. So this is bad. Okay, I'm going to draw a skull, but it doesn't work. So imagine the skull. So M will be greater than 1, causing distortion. Our preferred value for M is 0 to 1 because 0 to 100%. If it's greater than 100%, you're doing something wrong. Okay, so this is an example of AM, amplitude modulation. This is 50% modulation. You can see that this is, no, that's not it. Okay. So this is 50% modulation. What 50% means is 50% of the VC. Okay. Okay. How do I explain this? So if you can see over here and this value, they are equal. This is with respect to 0. Okay. Let's say this is 1 volt, right? If your modulating signal goes half of your carrier peak, half of your carrier peak, which means it goes down by 0.5 or goes up by 0.5, which is half of 1 volt. That is 50% modulation. 50% modulation. Okay. Let me rephrase that. If your modulating signal goes up or down 50% of the carrier wave, then it is 50% modulation. If I use voltage values, if your if your modulating signal is 0.5 volt and your carrier wave is 1 volt in peak, therefore you have a 50% modulation. Okay, it's just a ratio. What happens if it is a 100% modulation? Which means that your Vm is equal to Vc. Let's see. So this is Vc, original Vc, right? So this is also Vm, which means that this is 100% modulation because the value of V is the same. Here, the value is 0.5 of 1 volt. Shouldn't have drawn this. This is 0.5 volt of 1 volt. This is 1 volt of 1 volt. So 100% modulation. If it is greater than 100%, it's wrong. So let's see. You will see that this is not an envelope. It's overlapping. Remember, if we have overlapping modulating signal, skull, error message. So we don't want this. Okay. So this is above 100% and this is error. No overlapping for AM. Okay, so we talked about this. Kuih cara. If you're an international student and you haven't tried this, you're missing out. You find it somewhere in the stalls. We saw that overmodulation can produce something like this or something that is completely clipped off, like this kuih cara. So both are not good. Okay. One more slide and then I'm going to wrap it up. Bear with me just a little bit more. So we talked about modulation index. We also talked about modulation percentage. Remember, M is Vm over Vc. Assuming that Vc is always greater than Vm, our M will be from 0 to 100% or 0 to 1. So there is a way to calculate Vm and Vc as well as M using the wave that we obtain in lab. You will use the oscilloscope and you will tune some circuits and you will get a waveform that looks like this. And then I'm going to ask you calculate the Vm and calculate the Vc and calculate the M. So from the picture, you should be able to calculate them. So in this case, let's define a few terms so that we can do the calculation easier. So we have Vmax. This is Vmax. I think this is not really... Okay, I have a better picture. So this is Vmax. Okay, Vmax is from 0 to the maximum. Okay, 0 to the maximum. And then we have Vmin, 0 to the dip. We're talking about the positive side only. 0 to the maximum peak, 0 to the dip. So that is Vmax and that is Vmin. 0 to the dip, 0 to the max. So I'm going to write 0 here, like that, and like that. Okay, Vmax, Vmin. Okay. And then we have another term called Vmin peak to peak. Vmax peak to peak. So P dash P is peak to peak. So Vmin peak to peak is from, basically it covers both positive and negative signal. So basically it's just extending it all the way to the bottom. And then same case over here, from the peak down to the peak over here, from the dip down to the dip over here. Okay. peak to peak, dip to dip. Okay, so that's Vmin and Vmax. Okay, to find out Vm, okay, Vm is related to our modulating signal. The equation is Vmax minus Vmin divided by 2. Vmax divided by Vmin divided by 2. Let's see. Okay, bear with me a little bit more. Vmax is this, right? Vmax is this. And then you get rid of this. So what you're left is from here to here, right? Okay, you have Vmax minus Vmin. When Vmax minus Vmin, you're left with this reddish pink side. And then they ask you to divide by 2. Divide by 2. So what you're going to get is the modulating peak for the modulating voltage, the voltage peak for the modulating signal, which is Vm. Okay? Was that okay? So Vm is Vmax minus Vmin divided by 2. If you get a picture like this, you should be able to find it out. Okay, so what about Vc? Okay, so Vc, let's get rid of Vm first. Okay, last one, bear with me. This is the last slide. Vc is Vmax plus Vmin divided by 2. So let's find out what that means. So Vmax plus Vmin, which means that we are adding this guy as well. Okay. And then I'm dividing it by 2. Vmax plus Vmin plus divide by 2. Now, I don't know how to draw this. How do I draw this? I don't know. Let's just memorize the equation for now. So to find out M, remember the equation is Vm over Vc. So I use this Vmax minus Vmin over Vmax plus Vmin. I will get my modulation index. Okay, so that is the last slide for today. Let's do a little recap and just talk about what we talked about today. Okay, we talked about dBm. Remember dBm, you have to convert to milliwatt and then add the milliwatt together. Okay, sorry, I need to use this. Important message. dBm needs to be converted to milliwatt, and then you add the stuff in milliwatt or watt, and then only you convert back to dBm. So dBm is different than dB. dB you can add together, no problem. dBm, no, you cannot add them together. You have to convert it into linear scale and then convert it back to dBm if you want. And then we have a bunch of equations for dBm as well. Same log thing like attenuation and gain. Then we talked about the pattern for dBm. If it is multiplied by 10 in linear scale, you add 10 dBm. If it times by 2 in linear scale, plus 3. Divided by 2 minus 3, divided by 10 minus 10. Okay, and then we talked about noise. We have internal noise, thermal noise. We discussed thermal noise. We discussed the equation of a basic resistor in an open circuit. We also talked about short noise, which is independent of temperature but is dependent on current, bandwidth, and charge of electron. And then we have transit time noise, flicker noise. All of these are contributed by the components inside a circuit. And then we have correlated noise that we can actually predict, and sometimes we can filter them out. Correlated noise is harmonic as well as intermodulation distortion. You need to know what harmonic is. You need to know what is intermodulation distortion. Okay, and then we have external noise from machines, from the earth, from space. And then we also talked about signal to noise ratio. So SNR, we have linear scale. We also have in dB scale. So SNR is basically signal to noise ratio, which means that you have to divide signal with noise. And then we also talked about noise ratio and noise figure. Noise ratio is SNR input over output, or this guy. And then noise figure is in dB. Okay, and then we talked about the amplitude modulation concept, where we need two waves to make modulation happen. Modulating signal, carrier signal. Carrier signal has to have a higher frequency, higher voltage than modulating signal. And then when they are modulated together, you will get an AM wave. They are symmetrical. It basically mirrors the top modulating wave, and you get something that looks like that. And then we also talked about the equation, instantaneous carrier, instantaneous modulating signal, how to use it. And then I promised to have an example on how to use this. I need to do that later. And then the representation of an instantaneous AM wave, you need to know this equation. Okay. And then how to calculate modulation index and modulation percentage. And then I taught you how to intuitively understand how it looks like in waveform. And then we talked about overmodulation and distortion. And this was the equation that we finally discussed. And we will continue to discuss in the next class. So any questions before I end class? Everyone okay? Okay, don't save. All right. Okay, thank you everyone. I'll see you. Oh, tomorrow we won't have class, but I will be making a replacement class on Friday. I am so sorry. I am part of Innovaton, if you know what that is. It's basically a TV show. God. Okay, so Friday replacement class. I'll text you more on that. So I had someone raise their hand. Ada soalan ke? Tak ada. Okay, so that was an accident. All right, so I'll see you on Friday, not tomorrow. Tomorrow we don't have class. Bye, everyone. Have a great rest of the day.
Thank you, Doctor.
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 Doctor,
Yes.
I want to ask for ECC 3119 because in ESMP today we have lab from 2 to 5.
Oh, okay. So in week 1, I mentioned to you that the lab for this class is in week 4, 5, 6. Wait.
4, 5, 6, okay.
4, 5, 6, yes. So today is week 2, right?
Yeah.
So week 4, please come to I don't know if I want to put you in Monday or Wednesday. Which slot works for you? Monday 2 to 5 or Wednesday 2 to 5?
Both have class.
Both have class?
Yes. From Monday 2 to 4, I have ECC 4306. And Wednesday, I have ECC 5406.
Oh no.
4506, sorry.
Okay, can we discuss this in WhatsApp later?
Okay.
Okay.
Thank you,
Please
Doctor.
remind me if I forget. Okay?
Okay.
Okay, bye.